Welcome back all of you. In the last lecture we have started a new module that is on stress path, and we have seen what is the importance of stress path. Now we will move on to another particular aspect of stress path, that is how one can make the stress path plot meaningful. So let us start with today's lecture, and we will start with an example. So before moving on to the actual aspect of failure line in stress path, we will just try to see a simple example of a drained and undrained triaxial compression test which are given, and we have to plot the stress path in sigma A dash, sigma R dash plot, MIT plot and Cambridge plot. So we will see how the stress path will look like. Okay, so this is the data for the drained test, drained triaxial compression test, where sigma 1 is given 300, 400, 500, 565, 590, and sigma 3 is constant, which is 300, and back pressure is given as 100. I hope you remember what is meant by back pressure. And the undrained test results are given. Again there is an increase in sigma 1 and sigma 3 is constant, and at every instant of loading we have the pore water pressure as well. So this is how it looks like. So this is the preliminary data which is given. So let us first try with sigma A, sigma A dash, sigma R dash plot with a drained envelope. Okay, so this is the drained data which is given. Now is there anything to be changed in this? Yeah, first of all we need to understand, in the case of compression, sigma axial is equal to sigma 1. So we have written sigma A and sigma R now separately. Sigma A is the same as sigma 1 and sigma R is nothing but sigma 3, and for every sigma A it is 300. Then we have sigma A dash and sigma R dash. So there will be total and effective stress path, that hope you remember. For every loading there can be total stress path and effective stress path. Those which is plotted as per total stresses gives total stress path, and the other one gives effective stress path. So sigma A dash, sigma R dash is given. How did we get? Because there is a back pressure of 100 kilopascal, so we need to minus it. From all these, minus 100 will give sigma A dash, and sigma R minus 100, that is 200, gives sigma R dash. So how the plot will look like? So the plot will look like this. So sigma A dash on y axis and sigma R dash on x axis. So here the total stress is plotted. We can see that sigma A is increasing, sigma R is constant. So that is what is given, and sigma R dash is constant at 200 and sigma A dash keeps increasing. So this is increasing in this direction for both effective stress, and this is total stress as you can see here, and this is effective stress. So now what we can make out from this plot? Yes, we have plotted the variation in stresses as it progresses towards failure, but from this particular plot, what is that vital information that we are getting? In fact, we are missing something in this particular plot. So we will sum up in the end what is that we are missing. So now for the same triaxial compression, for the undrained test results. So we have undrained test results, and again we need to find out what is sigma A, sigma R. That remains same data, and 300 is the sigma R, but sigma A dash will change. Corresponding pore water pressure has to be detected. So that is how it looks like: 300 minus 100, 200, like 398 minus 232, 166. So sigma R dash, here you can see it is no longer constant. So, in initial case it was constant, now even though sigma r is constant, sigma r dash keeps changing. So, depending upon the pore water pressure. So, you can see that 300 minus 100 200, whereas 300 minus 232 68. So, how this particular stress path will look like. Now, the stress path has changed corresponding to drained and undrained. Now, things have changed, but you can note that the pattern of total stress path is more or less same, but total stress path is same, then the effective stress, how it changes in undrained test is totally different from what we have seen in the previous slide. Like both were vertically rising, but in this particular case you can see that it shifts towards left. Still, we are not able to make out much from this particular plot. Let us go ahead, because let us see, we will be as I told in the beginning, we will be considering three stress path plots, basically sigma A dash, then ST plot and QP plot. So, we will see for all the three how it looks like, then we will come back and summarize. So, next is TSS dash plot with the same data. So, drained data remains same, but whatever drained data we have seen in the previous slide. So, this one, so this is the drained data. Now, from this drained data we will have to find out what is the data for TSS dash plot, and we have the relationship for T and SS dash. So, that is given here. So, S and T is given for drained, and S dash will be this minus the back pressure is there. So, that will get changed, whereas in the case of T there is no change, as we have seen earlier that T is not affected by pore water pressure. So, then how the stress path will look like. Again, now the pattern of stress path has changed in TS plot. So, this is total stress and this is effective stress, but the pattern of both effective and total stress remains same in the case of drained stress path. So, corresponding undrained, so we have pore water pressure, so accordingly S will change, and we know that S dash is nothing but S minus U. So, that relationship we have seen. So, then 300 325, this is S, T is 0, this up to 49, that remains same even for effective stress, whereas total stress effective stress S dash will change. So, this is the data for ST and S dash T. So, how it will look like, again the pattern have changed. So, in this total stress path the pattern is more or less same, whereas in the case of effective stress it moves leftwards. So, this is how it looks like for TSS dash plot. Now, for QPP dash it is more or less same as that of ST plot. Again we need to find out P and Q. I hope you remember what is P and Q. If not, please refer back, and corresponding P dash is obtained and Q is obtained. Note that Q remains same, Q is equal to Q dash. So, in this particular case for the drained envelope it is very much similar to ST plot, and the pattern of both total stress and effective stress paths are same. Now, for the corresponding undrained case for PQ and P dash Q. Okay. So, that will give you again the total stress path maintains the same kind of pattern as that of drained, but in the undrained effective stress path moves towards left. Okay. So, we have now presented a very simple example how the total stress path and the effective stress path looks like in different stress path plots. Okay. So, now what we have understood from these stress path plots, why we are plotting this and why we are studying this. We want to understand when the soil will fail, or from the beginning how it traverses, how the stress changes up to its failure state. So, definitely that information is missing from whatever we have discussed till now. Now, there has to be a bound which gets attached to each of these stress path plots, without which this information is missing. Okay. So, that is the importance of today's lecture, failure lines in stress path plots. So, we will now get on to that, what is meant by failure line. So, it is need of failure line in stress path plot. What is the relevance of stress path plots? So, to make you understand this, we have explained the given examples. So, in all the three plots we have seen. So, what is the relevance of stress path plots? Locus of stress point means variation of any two stress parameters. So, that gives you a particular point. So, how this point changes. So, locus of stress path point is not relevant unless the bounds are defined. We should know, like, there is a space given to us, that is ST plot or QP plot or whatever. In that domain, what are the possibilities for these stresses to change for a given soil? This is very important. So, that is why it is told that we need to know the bounds within which the stress path points can change. So, that bound is defined by failure lines in each of the stress path plots. Failure can occur both in compression and extension. Normally, it's a general tendency that we discuss only about compression, and we do not really talk about extension, but we should also understand that extension is not like you are holding soil and pulling it apart. That is not the only case of extension. Extension can be created even by compressive stresses, the manner in which you are applying. I think some examples we have seen in module 2. So, here when we are discussing for stress path, we will discuss both, that is, one is the mirror image of the other. So, we will discuss both. So, failure can occur both in compression and extension. Failure lines corresponds to both compression and extension because of this. So, first let us see sigma A dash, sigma R dash. Now, I have already told you before that let us identify all these stresses in terms of axial stress and radial stress. The reason you will understand in this particular slide. So, here is a typical case of compression, where the triaxial compression what we generally do in the lab. So, this sigma 1 is the major principal stress, sigma 3 is the minor principal stress, the confining stress. Now, here let us see that both are compression, but here it is a case of extension. Why? Here you can see that sigma 1 is major and sigma 3 is minor. So, please understand that when there is a larger stress which is acting radially, it has a tendency to squeeze the soil apart. So, squeezing is just like a extension. So, same compression, but in a different manner of stress application can result in extension. Okay. So, that is what it is not the direct extension that we are talking about. Okay. So, these are two cases. Now, you can see that the axial stress in this and the axial stress in this is changing. So, depending upon whether it is compression or extension, sigma A dash will change, sigma R dash will change. So, according to Mohr-Coulomb failure envelope, now that is the only failure criterion that we know, that is Coulomb's envelope and the extended version or the modified version, which is the Mohr-Coulomb failure envelope. These are the failure criteria. We know how the soil will fail based on this. So, according to Mohr-Coulomb failure criterion, we know that sigma 1 dash is equal to sigma 3 dash tan square 45 plus phi dash by 2 plus 2 c dash tan 45 plus phi dash by 2. Now, for convenience, let us assume c dash to be 0, so that it becomes a bit simplified. Otherwise, also we know that c dash is a parameter that can happen only if there is cementation or if there is dilation. Okay. So, for the time being, let us consider c dash equal to 0. So, we can write sigma 1 dash is equal to sigma 3 dash tan square 45 plus phi dash by 2. Okay. So, sigma 1 dash by sigma 3 dash is equal to tan square 45 plus phi dash by 2, or we can rewrite this as 1 plus sin phi dash divided by 1 minus sin phi dash. We also need to have the reciprocal of this, sigma 3 dash by sigma 1 dash, which is cot square 45 plus phi dash by 2, or 1 minus sin phi dash by 1 plus sin phi dash. So, in a way we have now defined the failure lines in the sigma A dash plot. Now, for compression, we know that sigma 1 is the axial stress. So, this is the one which we have to take. So, sigma A dash by sigma R dash is equal to sigma 1 dash upon sigma 3 dash, which is equal to tan square 45 plus phi dash by 2. So, failure line is denoted as KFC, where C stands for compression. So, here sigma A dash, sigma R dash, this is the 45 degrees line, and then the KF compression line, that is the bounds of compression failure, is given by this line. So, this is nothing but the bound in compression failure. So, this line governs that any soil mass which is starting from any initial point in this domain has to fail here. So, there is no stress state which is possible for a given soil above this line. So, that is what it means. So, we have now defined one bound. Similarly, for the other bound, that is for the extension case, we know that extension sigma A dash is equal to sigma 3 dash. So, sigma A dash by sigma 3 dash, sigma A dash by sigma R dash is equal to sigma 3 dash upon sigma 1 dash cot square 45 plus phi dash by 2. So, that is the failure line for extension. So, KF extension. So, this is denoted by KF extension, and this is cot square 45 plus phi dash by 2, and here this is the bound in extension failure. Okay. So, this is how it will look like, and for example, if you take phi dash is equal to 30 degrees, then you substitute this, you will get Kf of compression will be equal to 3. So, that is more than this. This is only to show that the relative position of Kf compression and Kf extension with respect to isotropic line. Now, isotropic line you have K is equal to 1. Now, here Kf of compression is equal to 3. So, the slope will increase, and Kf of extension is 0.33. So, slope will be less than 1. So, the relative position of Kf compression and Kf extension is known. So, this is how it will look like. Now, any stress state that we have discussed in the previous slides, if you put, we know that where it should fail. Okay. Since the friction angle for that particular example is not given, we can find out and then we can see where it falls like. So, we will not get into that, just want to make sure that any initial point we know where the soil would fail. Now, in what manner it will fail, whether it is a straight upwards or moving towards left, it depends upon the type of the test. So, this is about sigma A dash, sigma R dash failure line. So, next we will come to TSS dash plot. Now, we have already discussed this in our previous lecture. If you remember the stress representation in module 2, we have touched upon MIT plot and we have derived the relationship between MIT plot and Mohr Coulomb failure envelope parameters. So, I will not take much time in this particular lecture. For compression, if you remember, we have obtained tan alpha equal to sin phi dash, where alpha is the inclination of origin of the line that joins the origin to the maximum shear stress points, because here C dash is 0. If you join all the maximum shear stress point, that line extended, that will give A dash is the intercept and alpha is the angle. So, if cohesion is present, so A will also be present. If cohesion is not present, A will not be present. But the inclination of the failure line is alpha, and tan alpha equals sin phi dash for compression we have already derived. So, this is how it looks like TSS dash, and we know that this is the isotropic line KF compression, here alpha is the angle. Okay. So, here the inclination is equal to sin phi dash, or the slope is equal to sin phi dash. Now, what about for extension? For extension we have not derived, so we will see that what will be the slope for extension. For that, T is equal to sigma A dash minus sigma R dash by 2. Now, for the extension, sigma A dash is equal to sigma 3 dash. Now, there are some important points or the minor points which we have to keep in mind. We need to know what stress is acting in axially or radially. So, in this case, sigma 3 dash is sigma A dash. So, sigma 3 dash minus sigma 1 dash by 2. If you take sigma 3 dash outside, we have 1 minus sigma 1 dash by sigma 3 dash by 2. So, sigma 3 dash is outside. So, that will give you sigma 1 dash minus sigma 3 dash is 1 plus sin phi dash by 1 minus sin phi dash. So, it will be 1 minus 1 plus sin phi dash upon 1 minus sin phi dash divided by 2. That will give minus here, if you bring it here, it will be 1 minus sin phi dash minus 1 minus sin phi. So, it will be minus 2 sin phi dash. If I write it here, this will be equal to minus 2 sin phi dash by 2 into sigma 3 dash upon 1 minus sin phi dash. So, that will give minus sigma 3 dash divided by 1 minus sin phi dash. Similarly, S dash is equal to sigma A dash plus sigma R dash by 2, same procedure, only thing is here the sign changes. So, it will finally give sigma 3 dash upon 1 minus sin phi dash. So, the slope, that is KF failure in extension, is T by S dash, that will be minus sin phi dash. So, that will give minus sin phi dash as the slope. So, we have defined the failure line in both TSS dash plot for both compression as well as extension. So, this is compression and this is extension. So, next is QP dash plot for compression. Again, this particular slope we have already defined in module 2 during stress representation, but for completeness I am just showing it. So, you have P dash is equal to sigma A dash plus 2 sigma R dash by 3. Again, if you take sigma 3 dash outside, it will be sigma 1 dash by sigma, remember this is compression. So, sigma A dash is equal to sigma 1 dash. So, sigma 3 dash if you take outside, it is sigma 3 dash by 3. So, sigma 1 dash by sigma 3 dash is 1 plus sin phi dash upon 1 minus sin phi dash plus 2. So, if you do the mathematical rearrangement, then you will get sigma 3 dash by 3 minus sin phi dash upon 1 minus sin phi dash. Q is equal to sigma A dash minus sigma R dash. You take sigma 3 dash outside. So, that will give 2 sigma 3 dash sin phi dash upon 1 minus sin phi dash. Kf of compression will get Q upon P dash, which is 6 sin phi dash upon 3 minus sin phi dash. Okay. So, this we have already derived before. Q upon P dash is 6 sin phi dash upon 3 minus sin phi dash. Now, for extension, P dash is sigma A dash plus 2 sigma R dash by 3, that is sigma 3 dash plus 2 sigma 1 dash by 3, you substituting the appropriate axial and radial stresses. Take sigma 3 dash outside, it will be 1 plus 2 1 plus sin phi dash upon 1 minus sin phi dash, that will give sigma 3 dash by 3 plus sin phi dash by 1 minus sin phi dash. Then Q is equal to sigma A dash minus sigma R dash. So, sigma 3 dash taking it outside, you have 1 minus 1 plus sin phi dash upon 1 minus sin phi dash, that will give minus 2 sigma 3 dash sin phi dash upon 1 minus sin phi dash. So, Kf of extension is q by p dash is equal to minus 6 sin phi dash divided by 3 plus sin phi dash. So, you can mark it, it is just the negative and the denominator, it instead of minus here it is plus. So, minus 6 sin phi dash upon 3 plus sin phi dash. So, what we have done for all the stress path plots, now the bounds are defined. Now, in whatever manner we need to study the stress path, we can do that. So, summary of today's lecture, the stress path is meaningful only if the bounds are defined. The bounds are defined in terms of failure lines, and in this lecture the failure lines are determined for sigma A dash, sigma R dash plot, T S dash, Q P dash for both compression and extension. So, that is all for today's lecture. In the next lecture, we will see what are the stress paths for common cases that we encounter, the common type of stress variations. We will try to see the stress path. Okay. So, that is all for now. Thank you.